So before I start, I'd just like to give a brief outline of how this presentation is going to go. So first I'm going to talk about the big picture and what this thesis is really about, then move on to talk about the optimal decision tree problem, the motivation behind this and why this research is important, the formulation of the problem, and then I'm going to present some results looking at synthetic data sets, real data sets, and also a medical application. So the big picture, this is a thesis in a field called data analytics, which as it sounds, you're given data and you try to analyze this data, you look for patterns in this data, and you can try to solve problems with data. This is quite a popular field, and it's actually becoming more popular, and that's due to the vast amount of data that is currently available. So Netflix uses data analytics to recommend movies, Amazon and all that stuff. So data is clearly, there's a lot of data on the internet, and then when you go to the doctor, for example, when the doctor is writing things on a laptop or an iPad, they're writing information about you, and all those electronic health records are going on a database that the doctors can then access. So the optimal decision tree problem looks at two different types of problems, classification and regression. So in a classification problem, we're given a lot of training data, which consists of independent variables and dependent variables, our x's and our y's. And our x's, or independent variables, have a number of features. So if the x is a patient's name, the features of that x would be the patient's age, their sex, the blood type, etc. And our y takes a value from 1 to k, and those are the classes. And the point of the classification problem is we're trying to create a function that's going to use the x's to predict and classify y's. So on the right is a nice diagram. This is what a decision tree looks like. And then the yes and the no are the two classes. So in this problem, we're trying to determine if an individual lives in the suburbs or not. So you start at the top of the decision tree at the age, and then age would be one of the features. And if the person is less than 30 years old, you'd move on to the left side. If the patient is older than 30 years old, you'd go to the right side, and you'd follow the tree down until you got to a yes or a no. And that would be your classes. A regression problem is somewhat similar, but instead of y being a class, y takes a real value. So think of the cost of a plane ticket. The cost of the plane ticket can be any real number. So currently, the state-of-the-art decision tree learner, the thing that's used to solve these problems, is something called CART, which stands for classification and regression trees. It's really popular. It has roughly 32,000 citations in academia and industry, which is a very large number. And how CART works is each split is based on a single feature. So as we saw in the previous the picture I showed you guys earlier, the age would be one of the features. And what CART does is it looks where it is in the tree, and it looks at all the features and all the potential splits, and whatever is going to improve the accuracy by the largest percentage, that's the split that's going to do. And that's something called the greedy approach. Now the issue with CART is that this greedy approach is flawed. And the reason it's flawed is because strong splits can be hidden behind weaker splits. So there could be a combination of splits that is going to improve the accuracy more. And this is where the optimal decision tree problem comes in. The optimal decision tree aims to create the tree all at once. So CART progressively makes each split in the optimal decision tree, creates the split all at once, which gets rid of the issue of the greedy approach. There have been several past attempts to solve this issue, notably linear programming, dynamic programming, and shallow optimal trees. We use something called mixed integer optimization, which is an optimization problem with linear objective function and linear constraints, where the decision variables take either a continuous or an integer value. And the reason we use mixed integer optimization is in the past roughly 25 years, we are able to solve these types of problems roughly 2.2 trillion times faster. So in the formulation of the problem, we want to minimize our misclassification error, and we also want to add a penalty. So in other words, we don't want our trees to be too large or too complicated, because then if we present that information to a doctor, let's say, it's going to be really hard for the doctor to analyze that. In most cases, we're going to split only on one feature. However, there will be some instances where we allow a split to split on several features, which would be something called a hyperplane split. So the first sort of tests we did was looking at synthetic data. Just to mention, this is regression. I'll give a classification example later on. So synthetic data is really commonly used, and it's really nice because it's data that the researcher actually creates. So it allows the researcher to change around the data to look at specific parts of your algorithm. And so when we were using synthetic data, we would first create a true tree. So we just make a random tree using our algorithm. And then we'd run through the tree and create all our independent and dependent variables. And those independent and dependent variables would create our data set. We then split our data set into 3 different components: the training set, the validation set, and the testing set. The training set is what our code uses to learn the algorithm and to create the algorithm. Then the validation set, which is 10% of the training set roughly, is what would be used to fine-tune all the parameters of that algorithm. And then the testing set is what we'd use to get our results. And we repeat this process several times, which allows us to better look at how we do. When we were first thinking about this, we considered 3 sort of main parameters. We looked at the min bucket value, the complexity parameter, and the regression parameter. When there's a decision tree, a lot of points are going to end up at the same end leaf node. And so the min bucket value is the minimum number of points at that leaf node in order for the tree to create it. And basically we do that, it helps with the complexity of the tree, because we don't want leaf nodes that only have 1 point there, we want leaf nodes that have like 500 points there. The complexity parameter is something our algorithm in CART uses to prune a tree. So after we create a decision tree, we actually go back up the decision tree, and we say if this split doesn't improve the overall accuracy by a certain threshold, the complexity parameter value, we get rid of that split. And finally, the regression parameter is the number of elements used to predict the dependent variable at the end of the tree. And that's for regression problems where when we get all the way to the bottom, instead of giving a class, we actually give a function that's going to tell us the value. In the results that I'll show soon, we compare 4 different trees. So we look at the true tree, which is the tree that we created to create the data set. We look at CART, which is the tree built using the CART method, CART-D, which is the tree built using the CART method, but with a restricted depth. So we restrict the depth of CART, and we don't want CART to be too large. And then OPT, which is the tree built using our algorithm. When we report results, we report the in-sample loss, the out-of-sample loss, the tree size, the maximum depth, the average depth, and the dynamic complexity. The in-sample loss is a loss function, or the misclassification error, averaged over all leaf nodes of the tree evaluated on the training set. The out-of-sample loss is essentially the same thing, but it's evaluated on the testing set. The tree size, the maximum depth, and the average depth are pretty straightforward, so I'll leave those. And the dynamic complexity is basically a weighted average depth. Throughout this process, we looked at changing different variables and seeing how our algorithm responds. So we looked at changing the amount of noise added to both the independent and the dependent variables. So what that means is when we first create our tree and we get our x and our y's, we adjust the value of the independent variable or the dependent variable slightly to see how our algorithm performs. We also looked at changing the number of training points, and the reasoning behind that was because often you won't actually have that many sample points when conducting a study, so we wanted to see, does that actually make that much of a difference? Here are 2 tables. The one on the left is when we add noise to the features or the independent variables, and the one on the right is when we add noise to the dependent variables or the y. So on the left we have our method, we have the percentage of noise added, out-of-sample loss, and so forth. Just some observations about the previous 2 pictures. The in-sample loss increases with the noise, so the more noise we add, the larger our in-sample loss becomes. Our out-of-sample loss, however, is more robust. Our algorithm, so the optimal trees method, outperforms both CART and CART-D. Furthermore, it's quite interesting that our method actually gives similar depth characteristics to the true tree, whereas CART and CART-D often give larger trees. And that's really nice to know because it tells us that we're closer to the ideal solution. And furthermore, the results are robust to the number of training points. So we can see in the previous slide that even when we have a small number of training points, we can still get good results. We also ran a couple of tests using hyperplanes, so that means that we allow our decision trees to split on using multiple features, but this didn't actually improve our results too much, and we believe this is mostly to the fact that our true tree was still created using parallel splits or single splits. We then looked at some real data sets. Again, this is looking at a regression problem. So we looked at roughly 38 total data sets from some online repositories. They were very nice. The number of training points ranged from 16,000 to 41,000. The number of features ranged from 2 to 122. So we had a lot of different things to look at. Here we were running a newer and a faster version of the algorithm. So we had adjusted it and fine-tuned it slightly from the previous tests. When we did all these tests, we set the regression parameter equal to 0, which allowed us to make a direct comparison between the greedy method, CART, and the non-greedy method, our algorithm. Here's a summary. So on the left, we have this column called maximum depth. And so at a maximum depth of 10, we allow both CART and our algorithm to choose a depth anywhere from 1 to 10. At a maximum depth of 5, we allow CART and our algorithm to choose a maximum depth of anywhere from 1 to 5, and so on. We give the number of times CART outperforms our algorithm, number of times our algorithm outperforms CART, number of ties, the accuracy improvement percentage, and also the p-value. The p-value is a measurement that allows us to look at the statistical significance of these results. So our method actually improves the average accuracy for almost all values of the maximum depth, which is very nice. However, the improvements are not consistent. So in some situations, we improve the accuracy by 5%. In other cases, we improve the accuracy by only 0.5%. And furthermore, the improvements are not statistically significant, and that's by looking at the p-values. The last study we did is we looked at a medical application. This is a classification problem, and here you're trying to determine if a patient is at high risk or low risk of something called clinically important traumatic brain injury. Typically, if someone gets a brain injury, they'll go to the doctor, and the doctor will ask that patient to go take a CT scan. And CT scans are very commonly used. However, the CT scan actually emits radiation, which can be potentially harmful and even lethal to younger patients. So we looked at a past study that looked at patients under 18 years of age from 25 different emergency departments. The total number of patients was 42,412. The original study that did this divided the children into two categories: children that were younger than 2 years of age and children that were older than 2 years of age. And for each of those two categories, they gave roughly 6 predictors that could tell a doctor if this patient is low or high risk. And so we're setting out to improve this and give more accurate results. So we use the same data set, and we considered roughly 120 independent variables. Looking at the data, it's important to see that we have something called an imbalanced problem. That means that fewer patients had this clinically important traumatic brain injury than patients that did not have this. So to look at these two different types of problems, you can do something called undersampling or oversampling. Undersampling would be if, for example, we have 100 patients that are high risk and 500 that are low risk. We take 90 of each category. Oversampling would be we take 300 of each category. And in order to get 300 patients that are at high risk, we take the 100 patients that are at high risk and look at them 3 different times. And we looked at different ratios, both for undersampling and oversampling. Here are a couple examples of independent variables. So they're pretty just standard things that a doctor would know about you: your age, ethnicity, gender, race. And then we look at, the severity of the injury. Was the individual dizzy? Did they vomit? And so on. When we report the results, we report the true positive fraction. So did we correctly identify the patients at high risk of clinically important traumatic brain injury? The true negative fraction, did we correctly identify those at low risk? The AUC value, the Breyer score, and the class conditional Breyer score. The AUC value, the Breyer score, and the class conditional Breyer score are just 3 different ways of looking at the efficiency of the classifier. And finally, we presented the accuracy. So here are 2 tables looking at oversampling with a 1-to-1 ratio. So we had, in the first case over here, we had 1,000 patients that had that were at high risk, and 1,000 patients that were low risk. In all cases, our method actually outperforms CART by up to 2%, which is very, very nice. Furthermore, it's important to know that our method performs well even with only 2,000 total samples. And again, this is going back to the synthetic data set where we showed that we can do well even with a small number of patients. Our method also increases the true positive fraction, which leads to lives saved, and it increases the true negative fraction, which leads to an overall decrease in the exposure to radiation. Here's a picture of oversampling with a 1:n ratio. So in the first case, the 3,000, we had 1,000 patients that were high risk and 2,000 that were low risk, and so on. Again, our method outperforms CART in all cases. However, the true positive fraction actually decreases slightly, while the true negative fraction increases. Here's a table looking at undersampling. So undersampling would be, for example, in the example with 100 at high risk, 500 with low risk, we look at 90 of each. And here we didn't actually get as strong results, although our true negative fraction is quite large. So to summarize the past 3 slides, our method has up to a 2% improvement in all cases for the overall accuracy. Our method works well even with relatively small samples of even 2,000 children. Furthermore, in this application, oversampling worked better than undersampling. We do have some suggestions for future work. We suggest looking at different ratios. So we considered cases of 1:1, 1:2, 1:3, 1:4, and 1:5. So there are different combinations of these numbers that could give better results. We also suggest looking at the specifics of the optimal tree solution. So similar to how the doctors gave us 6 predictors to determine if a patient was at high risk or low risk, it would be nice to look at our solution and give something similar. Before I end, I'd like to thank my senior thesis advisor at MIT, Professor Dimitris Bertsimas, and his student Jack Dunn, with whom I worked extensively with. I'd also like to thank my BUA senior thesis advisor, Mr. Daniel Ford, and my thesis group. And I'd finally like to thank my family and friends for keeping me on the track through this year-long process. Thank you.
Very nicely done. Questions for Aris? Well,
so the key things, it was the question that what are the key things that our method from CART? So the key thing that we're looking at is we're trying to solve this greedy approach in flaw, where CART, there can be stronger splits hidden behind the weaker splits. So we're looking to create the tree all at once, which proves to be a difficult problem because there are a lot of variables to consider and there are tons of different combinations. And so that's the main thing. We're trying to create the tree all at once, which will hopefully give the most accurate results or the best results.
questions?
So if I understand you correctly, CART does the splits sequentially, like one at a time, and it's usually a bad one for like a one with poor predictive power and then one with good predictive power. That kind of corrects the usefulness of the tree, is that correct?
Yeah, so CART,
So what you guys are doing is trying to pick the whole tree at once so that you can have the splits sort of in order of usefulness.
exactly. So CART goes sequentially. And so what I mean by a stronger split behind a weaker split is if you look at the particular situation that you're in, so if CART is in a particular place in the decision tree, there could be a split that increases the overall performance of the tree by 5%. However, there could be a weaker split that maybe only increases the performance by 3%, but because you chose that weaker split, later on, there's an even stronger split that increases the overall performance by even 10%.
Other questions?
P is the size of your input vector.
Yes, P is the number of features.
So what happens to these are all the part P's of 100,000?
We didn't go that high. Typically, the larger P is, the more difficult the problem is, and so the longer it takes to solve. And so when we were running synthetic data sets, which was kind of like the first iteration of the algorithm, even a small P and a small maximum depth could take several hours to complete. So there were definitely days where I was sitting at the lab, like waiting like several hours for this to run through. Whereas with the newer version of the algorithm, even with larger p-values and a larger depth, it could still run much quicker.
Any other questions for us? Zach?
What's the next step for the email?
So the next step is the Jack Dunn, the PhD graduate or candidate who I was working with, is publishing a book. So if you guys are interested in that, I would definitely recommend the book. So the next steps is there, of course, much work needs to be done in this. So far, this mixed integer optimization approach that we're trying to take seems to be quite successful. And in most of the tests that we do, we actually outperform CART and some other methods that can be used to solve these problems. I don't know if anyone knows of these, random forests, so forth. So hopefully just trying to, make sure more people are aware to these methods, and hopefully more people will hop on the train and try to solve this problem.
All right. Very nicely done, Iris.